Right. So I'm going to share my presentation for today. So I would assume that all of you can see my presentation. And by the way, there were some of you telling me that you had issues logging in and looking at the shared screen. So for that, I guess the best make sure that one thing is to make sure that you have the most updated version of the software, right? Which is Zoom. So make sure that you have that before you log in next time. Right. So as a summary, yesterday I discussed different types of telescopes that we used in astronomy. And so you probably know right now that there are these large telescopes that astronomers used to build for research purposes. And these telescopes are not only for optical region of the electromagnetic spectrum. So there are telescopes that astronomers have built so that they can use those telescopes for other wavelengths, right? And so one of those that I discussed last time is about this radio telescopes, right? So this is where I actually stopped. So remember that, let me just do a bit of revision. So remember we were talking about radio telescopes, and I discussed why radio telescopes are so large. So that's basically because the wavelength is larger for the radio wavelength, which means to get a good smaller diffraction limit, you need to have very large disks in these radio telescopes. And one of those example for one of those telescopes is actually this Arecibo telescope, which has a disk with a diameter of around 305 meters. But unfortunately, this particular telescope actually has collapsed 2 months ago. I mean, when I was making these presentations, it was there, but after, within the last month or month before the last month, close to the end of November and early December, this particular telescope has actually collapsed. And because of that, this is no more not anymore under working condition, so that there is no way that you can use it right now. But as a solution, there is another large telescope, a radio telescope in China. So they have decided few days ago actually, so they have this large 500-meter spherical telescope which they call as FAST. So they make it available for international scientists as well, right? So basically, when you have a telescope, you divide the time who is going to use it at a particular time location. So the China has decided to give 10% of their time to these international astronomers, so that people who are used to Arecibo telescope, maybe now they can use this telescope in China, right? And there is a YouTube link that I have posted here. So if anybody is, you have to go to that link and just get an idea how the Chinese telescope looks like in this radio astronomy. Right. So apart from that, actually, I have also talked about the advantages of radio telescopes yesterday, and then there is another method called interferometry that people use to do radio observations under radio wavelength. So that is actually a method that they use by having a separate array of telescopes and then use this theory of interferometry to operate that. And this is actually some pictures of different interferometric, different radio telescopes that operate as arrays. And then this is actually one picture that I showed you last time. of the galaxy NGC 1316, and this is a combination of different wavelengths taken from different clusters. And for the radio emission, these orange type two lobes that you see in the two sides of the galaxy are actually the coming from the radio emission, right, which you have to observe from a radio telescope. And this part actually has observed from this very large array, which is again an array of telescopes in New Mexico. And now if you look, think about the size of these lobes, actually one is close to 600,000 light years, right, across. Right. Now, so that's about observing under radio wavelength using radio telescopes. And then there is another branch in astronomy which we called as infrared astronomy. And that is observing under these infrared wavelengths. You know that if you look at the electromagnetic spectrum, you can see this infrared wavelength. Now this infrared, there are several telescopes that we have on the in the space to observe under this infrared wavelength. So the first of those was actually the Infrared Astronomical Satellite, or IRAS, which was placed in the orbit in 1983. And then after that, there is this next telescope called Spitzer Space Telescope. Maybe some of you may have heard about this word as well. And this was launched in 2003. And so this has actually revolutionized the infrared astronomy. And remember that all these telescopes are in the space, right? Because these are infrared, working under infrared wavelength, which you cannot, observe from Earth. And then we have this stratospheric observatory for infrared astronomy, or we used to tell this as SOFIA telescope. And this is a very, very unique telescope that is actually built inside a Boeing 747 airplane. So what actually happens here is the airplane is flying all over the world with this telescope, right? So which means it's kind of a free telescope that you can take data from anywhere. So it basically it's not in not in an orbit, but it's up in the space traveling with this Boeing 747 airplane, and it can take data without based on the location, right? Because it can travel all around the world as needed. So that's one of the very interesting telescopes that we have under infrared astronomy. And the next one is actually the one that is planned to actually start its operations in this year. This is called James Webb Space Telescope, or JWST, right? Probably when this start operates, you probably will see this even in the TV. And I guess this maybe start around September if everything happens as planned, because initially they actually planned to start this in 2018, and due to several technical reasons and other stuffs, they had to postpone it until this year to finish the work. And this is actually a very specific telescope, and scientists or astronomers think that this will be the replacement for the Hubble Space Telescope, because Hubble Space Telescope was launched around 1990, and it has been 30 years now for the Hubble Space Telescope. And so they have basically NASA, so they have basically stopped supporting and repairing this Hubble Space Telescope from 2009, as far as I remember, because it cost a lot of money. If you need to repair a telescope that is in one of these orbits, so you have to send astronomers there and do the repairs, and then they have to come back again. And because of that, they have decided not to support for this Hubble Space Telescope. Instead, they have put money to make this large James Webb Space Telescope. Now, the special thing about this is compared to Hubble Space Telescope, Hubble Space Telescope had a primary mirror which had a diameter of 2.4 meters. Now, this particular telescope will have a primary mirror that has a diameter equal to 6.5 meters, right? So which will be interesting. And with this kind of telescope and also in the space, having it in the space, then can do actually wonders for the astronomy. And so there is again a YouTube link, which is a very nice, it will give you a very nice explanation about this Hubble Space Telescope, James Webb Telescope. I don't know whether, let me try to share this screen if possible. Yes. So this is actually that particular telescope. So let me just reduce the frame rate so that you won't get obstructed. So this is the James Webb Telescope. So I'm not going to play the sound here. And you can see that this particular telescope, they have this large 6.5 meter mirror. And so it's basically, you know, this whole telescope can be taken in this way through a spacecraft. So what they have done is actually they use this origami methods. You know, this origami that you can fold everything and unfold it after to make a nice picture, some kind of Japanese thing that you probably heard about this. And this particular telescope has made in that way that it will unfold all its mirrors, make it to larger telescope at the space, right? So that's how it works. So this is kind of a artistic view of that. And here are some of the people that talks about this James Webb telescope. And just go through this video and see it. It will be very interesting one for you. And I will probably have I mean this I will, when I make questions for you, I used to make also consider these videos, right? So they are part of your lecture, so make sure that you go and look at that video. So I'm not going to play the complete thing because of the time limitation, and there is no point of playing it here because you can see it even from the internet once you have the link. So I would let me just post the link to your chat as well, but it will be in the PowerPoint presentation once it is uploaded, right? So let me copy it and then paste it to the chat. This will be actually that particular story about the telescope. Oh, let me share my presentation back. And so you will probably see some details about James Webb Telescope, some more details under this section. And the first one is the iris. So I'm just going to explain one by one three of these telescopes that I have in the previous slide. And the first one is what we called as the iris, right? Iris is actually also called as infrared astronomical satellite. So this was the first orbiting observatory. First orbiting infrared observatory that is launched in 1983. So this was basically in the space orbiting, and then this was equipped with a mirror that has a diameter of 0.6 meters, and you can see how small the mirrors for space telescopes by that time, like in 1983. And this is cooled to a temperature less than 10 Kelvin. And then IRIS is carried out, the primary task was was to carry out rapid but comprehensive survey of entire infrared sky over a 10-month period, and it has actually catalogued around 350,000 objects which emit infrared radiation, right? So this catalog is available for anyone for free to use now, and that is the basic operation and what IRIS did for infrared astronomy. And the next one is actually Spitzer Space Telescope, and this one is in fact most powerful, one of the most powerful telescopes, and this has zero at that time, so it's 0.85 meters Spitzer meter the primary mirror, and this is launched in 2003. And actually with these infrared observations, the astronomers can detect a cooler part of the cosmic objects, because when it cool, it will emit infrared, and such as the dust clouds around the star nurseries and remnant of dying stars, those kind of things you can get from infrared astronomy. Right, so these are actually some examples that were observed by Spitzer Space Telescope. Now, one of these actually a region of star formation and the remnant of an exploded star, and a region where an old star is losing its outer shell. So these are the three scenarios. One in the left corner is actually a region of a star formation, and then the one in the middle is actually the remnant of an exploded star. And then the region where an older star is losing its outer shell, we also call these as nebulas, is what you see in the one in the right hand side, and this is to be precise, this is called as the helix nebula, right? So we will also talk about the nebulas under one of the sections when we are talking about star formation, right? Now you will not see these objects in this way using optical telescopes, and also our eyes are not sensitive to infrared rays, so we can't look at these images in this way from our naked eye or using optical telescopes, right? This can be done using only these infrared telescopes, right? Now you can see that there are different colors that you have in these images. So these colors are actually selected by astronomers to highlight the details like the temperature, high and low regions, and those kind of things. And this is just an image of a Spitzer telescope. Now this is actually the Orion Nebula, you probably have heard, in the infrared region. So from infrared, what you see is a lot of star formation regions when you have a lot of infrared waves, so energy coming out from that. And why is that? We will learn about that in under the star forming when we are learning about stars. Why you have infrared wavelengths when you have star formation regions, right? And again, you can see clearly that this is Andromeda galaxy, by the way, and the picture in the above image is the galaxy under optical wavelengths, and the same galaxy is once observed using infrared wavelength, what you can see is one in the below picture, and you can see a lot of red dots in that infrared region which you cannot see from the optical telescope, right? Now this is what actually you have to understand, at why we are using these different wavelength regions, right? From this lower image you should be able to see that a lot of things that you cannot see or doesn't visible in optical region, you can see it from infrared wavelengths, right? Right. So this is the the third telescope that I was talking with you, the Sophia, and this is an airborne telescope, and again I'm doing infrared observations. Now the reason that you observe this infrared observation from the space is that the Earth blocks most of the radiations, right, at these wavelengths, right, because they are shorter wavelengths, and we can only make direct ultraviolet, X-ray, and gamma ray observations from space. And also for the X-ray, gamma ray, so you can't even think about observing these observations from space. Sorry, from the ground, right? You have to go into those space. And this particular telescope, which we called as Sophia, is actually a large 2.5 meter telescope, and the long name for this one is Stratospheric Observatory for Infrared Astronomy, and we call that this as Sophia. Actually, the telescope is inside a Boeing 747 airplane, so that when airplane flies, so airplane will fly with this telescope, and it will make observations, and all these computers and the technology that needs to handle is already inside this particular airplane with some professional astronomers who are operating and analyzing this data, right? And the advantage is actually it can travel through around the world, so that it can it is like a portable telescope that you can go anywhere with that and take data from the space, right? Now, one of the major discoveries actually this particular telescope did in very recent, probably I guess 3 or 4 months ago, is the that they found the evidence for water on this sunlit surface of the moon. So that's one of the major discoveries that it made, right? And now let's go and talk about. Oh, by the way, and there is a an YouTube video again about Sophia. So if you click on this link, so let me see whether I can take. I will again post the same link for you. We have it before I share the screen again. This is actually the Sophia telescope, right? So let me share my screen again. Probably you can go to the into that link and see how this Sophia telescope works, which will be very interesting for you, because you probably have seen this for the first time in your life. That telescope is operating inside the Boeing 747 airplane, right? And next we will talk about James Webb telescope. So here is an artistic image how the James Webb telescope looks like, and uh, so this is an orbiting infrared observatory basically, and this will complement and extend the discoveries of the Hubble Space Telescope. Basically, Hubble was the giant that was in the okay. So one of you again telling that you can't see my screen. Let me stop sharing and reshare the screen. right? So can someone can okay, so this is the one that who had this issue, the problem with this Zoom sharing option. Right. Now the James Webb Telescope is actually a replacement for the Hubble telescope, but this will actually do a lot of other more things even Hubble telescope cannot think about, right? The advantage is actually with this larger mirror and also with new sensitive cameras and all these technologies, we expect that the Hubble telescope would be able to look at uh, uh, the first galaxies that are actually formed in the universe, right? You know that in physics or in astronomy, we will learn about in cosmology about this theory of Big Bang, so which basically explain how the universe started initially with these unified forces and then have something called inflation of the universe and then move on to a next phase which we called as radiation era, and then it has converted to a matter domination era, and then while all these things are happening, firstly hydrogen and helium formed, and then they have made these galaxies formed after some time. But up to now we have not seen these very earlier galaxies, the galaxies that are just formed in the initial steps, right? So we expect that this particular telescope will be able to show us galaxies that are like billions of years away from us because of the sensitivity of these new instruments and because of this large mirror, and at the same time the advantage of avoiding the atmosphere so that you will not have atmospheric seeing in here, right? So here are the major science themes in the James Webb telescope, and you can see that scientists have already have made keep lot of faith or hopes on James Webb telescope to do discoveries that we haven't been doing up to now. One of those science goals is actually the first one is the first light and the reionization. So that what does that mean is actually we expect that the James Webb will be a powerful time machine with infrared vision, right? So that will peer back to over to 13.5 billion years to see the first stars and galaxies forming out of the darkness of the early universe. So what that means is that we expect that the James Webb telescope will be capable of acting as a very powerful time machine so that it can look at the things that are 13.5 billion light years away. This is just like maybe after zero point 0.1 billion years after the formation or after the Big Bang, so that you will see very early type galaxies. Right? Early type means very earlier galaxies that are forming. And at the same time, so its unprecedented infrared sensitivity will help astronomers to compare the faint galaxies and earliest galaxies to today's grand spirals and ellipticals. So this is a different story that you probably may not understand right now. That because it has a very high infrared sensitivity, so it will probably give us a good chance to compare these faintest galaxies and also earliest galaxies to today's grand spirals and ellipticals. So what you can see from an optical telescope today is spirals and ellipticals, but what we would expect is when you go back to very early times, there may be no spirals or ellipticals at that time, right? Because galaxies evolve and may have become to these spirals and ellipticals later. So maybe these galaxies may have a complete different type or different shape at that time. So we will observe those kind of things using this particular telescope. And also we will observe about the birth of stars and the planetary systems, and then the origin of our life and the planets. So those are the science goals actually uh, that you would have to think about, right? Right. Now let me go into the others. Now we have talked about infrared astronomy and then radio astronomy, and then this is another division of astronomy which we called as ultraviolet astronomy, right? Now Earth's atmosphere is basically or completely opaque to most of the ultraviolet radiation. There is a small narrow band that you can still observe from the Earth, but this is not as actually good or clear as the optical region that we are observing. And so Earth basically, so the most of these ultraviolet radiations, they are opaque uh, to our atmosphere, right? So which means they doesn't go through the atmosphere. So we have to go to the space again to make these observations for ultraviolet region. And so there are several telescopes that have built to make observations under this ultraviolet region. And one such one such instrument is International Ultraviolet Explorer, or IUE. So this is collected data from 1972 to 1996. So you can see that this is a fairly older one. And this actually revolutionized this UV astronomy. And then we have Extreme Ultraviolet Explorer, which was launched in 1992 to take data, and this mission is completed in 2001. And one of the very recent and very popular uh, surveys that is conducted under ultraviolet astronomy is this Galaxy Evolution Explorer, or GALEX, right? So this was launched in 2003 and worked until 2012. And this has actually done a lot of things and have taken a lot of data. So this had a 50 centimeter primary mirror, which is close to half a meter. And this is actually a nice example what ultraviolet can do for you. And this image is an image of a cartwheel galaxy. So this cartwheel galaxy is one of like a very popular galaxies that you can see. And this in particular image under this violet color is what you see the ultraviolet regions, right? And you can see this all these outer shells in these galaxy. Basically the sorry, so let me show you the which one is actually the cartwheel galaxy. So this is actually the cartwheel galaxy. And this particular galaxy, actually we are thinking that maybe it has merged, so it is going to merge with this particular galaxy in one day. And you can see this violet color that goes around this cartwheel galaxy. So those are the regions that are captured by from ultraviolet astronomy, right? So these are actually basically star forming regions for a reason. That is because when you have a lot of star forming regions, those regions used to emit ultraviolet radiation. And you may be learning this why it happens like this in the sections when we are talking about star formation in next chapters, right? Probably starting from the 15th after next week maybe, right? and uh, and also there are other colors that are combined to this picture, and those are coming from different wavelengths like X-ray and maybe optical wavelengths like that. So it's like a composite image from different wavelengths, right? And then we have, so remember we have talked radio astronomy, then infrared astronomy. Now we have been talking, and we just finished talking ultraviolet. And then there is another section called high energy astronomy. And high energy astronomy means actually shorter wavelength astronomy, that is about doing observations using X-ray and gamma ray telescopes, right? And these observations actually present a new technical challenges because these high energy radiations, they tend to penetrate mirrors, right? Normally, you know that when you observe under optical regions, normal these light rays, they just come and hit the mirror and then get reflected, right? But these high energy photons or X-ray, and specifically X-ray and gamma rays, they don't like reflect. Instead, they will penetrate through the mirrors, right? And because of that, we will this particular region, which we called as high energy astronomy, they use different techniques to make these telescopes. And you will see one of those examples. I am not going to explain all these things. And the universe actually gives off much less light at these wavelengths compared to the radio and optical wavelengths. And there are few examples for those kind of telescopes. Now the Einstein Rosat and XMM Newton and Chandra X-ray are some of the examples for the telescopes that works in this particular region, especially for X-ray observations. And for the gamma ray observations, the gamma ray telescopes such as the Fermi Gamma Ray Space Telescope is one of the very successful telescopes that we have right now. And this is some information about Chandra X-ray telescope. Now you can see that there is a source right here which emit X-rays, and then you have to capture it by the Chandra X-ray telescope, and it has these nested 4 layers like this, right? And instead of just directly hitting to those layers, what it has, what is this particular thing is doing is it has a small angle which we call as a glazing angle. So once it is hit, it will slow down and then go in a path like this, so that you will see X-rays in this particular site. So don't think that everything is this doesn't work as how optical telescopes work, right? Because it's hard to get these rays reflected, so they are using a different mechanism. And this is just an image when Chandra is launched in 1999. So Chandra X-ray telescope is a very, very popular one in the space for X-ray observations. And you may not have idea about these nebulas. Nebulas actually again related to star formations. We will talk in about that in this particular section. But in general, you probably have heard about this word nebula, and this is an image of the Crab Nebula in was taken from Chandra X-ray Observatory, And basically nebula is actually something that remains after supernova explosion, right? Then the supernova explosion is, in brief, is like a explosion of a star. I mean, it comes to towards its towards the end of its lifetime, right? And these supernovas are created in different ways and different types. We will talk about those later. But this is a nebula, which is like a remnant after a supernova explosion. And this image is taken completely from an X-ray telescope, but you can get the same image in using different telescopes. Now this first one is the X-ray image of the Crab Nebula, and the same image when you take from the visible telescope under visible light. So this is how it looks like, right? It's completely different. And under infrared, this is the same picture under infrared wavelength, and this is the same picture under radio wavelength. Now you can now understand that why these observations from different wavelength regions for different wavelength regions in the electromagnetic spectrum is very important, right? So they give different kinds of information, right, depending on the wavelength. And you can see from visually, you can see that from these four pictures, they are completely different and give unique different kinds of information under different wavelengths, right? Now this is why astronomers actually observe these astronomical objects not only using the optical wave length region, but also using other wavelengths such as X-ray, visible, infrared, and radio astronomy, and sometimes ultraviolet, right? So all these different wavelengths give you amazing different information about the same object, right? And there are certain objects actually they don't even emit visible light in the visible region, so that you have to go for other wavelengths to look at those, right? Right. So let me. Now this is how Jupiter looks like from Chandra, from a Chandra X-ray telescope. You can see that it's not that much details, but you can still have some two regions like this, and some other regions visible under X-ray wavelengths. Right. So this is actually a X-ray flare from the black hole actually at the center of our solar system, right? So you know that I have mentioned this in the first day. Every galaxy has a supermassive black hole at the center of the galaxy, right? Now in our galaxy we have one such black hole, and this is the X-ray flare coming from that particular black hole. And this center is about 4 million solar, I mean this has a mass about 4 million solar masses for this particular black hole. You can think about the size of that, right? So that's why they are called supermassive black holes. Right, so this is again a composite image from X-ray, infrared, and optical observations. And right at the center, you will see that there are four galaxies actually merging together. And these different colors that you see in the image actually is usually interprets different wavelength regions. For example, so as I have mentioned here, this is a collision of four galaxies, and so this is actually infrared data from Spitzer telescope, which is shown in red color, and visible light data is from a telescope called WIN telescope, which is again situated in Arizona, and they are from green color. Maybe I'm not sure that you can see all these colors very clearly. And then X-rays appear to be blue from the Chandra X-ray telescope, right? So you astronomers basically combined all this information to get an idea about a particular object. right? So that's how it works, right? And then for the last section of this one, we have also used gamma ray observations in astronomy. And this is actually Fermi Gamma Ray Space Telescope, which is again in the space taking data. And so that's, I'm not going to talk much about the Gamma Ray telescopes, but just keep in mind that they are there. And this particular last slide of my lecture for this particular section about electromagnetic and telescopes basically summarize why we go for observations to the space, right? You can see that this is a mountain top right here, right here. So only a certain range of wavelength that used to come into mountain, even to mountain tops for observation. So it starts from a part somewhere here. Radio and microwave, they don't have any issues until the visible region. And then once you go into the IR, I mean, they partially comes, but not that much, right? So you have to eliminate that part. And then you have, of course, the visible light right here. Visible light you can observe from Earth. So that's why these lines have moved up to here until this position, right? And then the ultraviolet X-ray and gamma rays, those rays even don't come into the Earth. There is a small region after, just after the visible light, that you may get some information from the ultraviolet region. Other than that, basically the ultraviolet also is something that you have to make observations from the space. But there are few places like a Wynn Observatory in Kitt National Observatory that you have some facility to observe these ultraviolet band, but it's a very narrow band and not that much easy to take data from that. And all the other wavelength regions such as X-ray and gamma ray and also most part of the ultraviolet again are actually that you have to make observations from the space, right? So that's the difference, right? So this is like the take-home message for you, which basically summarize everything that I talked about different telescopes and why they are not, why some of they are in the space rather than keeping them on the Earth, right? Right. This actually basically explains the idea about electromagnetic spectrum and telescopes, right? Basically, this is the instrumentation part of your lecture, and there may be few slides that I still have to explain about how to choose a telescope and so, which I promise to do for you. So I will do this probably that particular small section with the next sections probably towards the end of the next week, right? Because I have a different computer that have to take that slide from there. And anybody have any questions up to here before we move into the next section? So I will actually I will probably stop the lecture today within I mean after 1 hour, because I am going to start a new section which I will talk about other worlds. So other worlds means they are I mean about the other planets basically in our solar system. So that will be the next section. So under that section I will talk about different techniques that we use to find the nature of surfaces of different planets and how you categorize planets. Those kind of things we will learn under the next section, right? And how to find the mass of a planet and different properties of planets, and then a little bit of information about the moon and sun. So that will be the next section that I will talk before I am starting talking about stars, right? Anybody have any questions up to here that we did? Right. So please make sure that if you have any questions that you need to ask and make those things clear, right?